There is this insidious thing in most analyses that you cannot trust them for the full 100%. It has to do with how they are built up, but it has some very serious implications for how we use tests and when. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And I've had this video, a couple of videos already about SPC, but one of my last videos was about there is a chance that your SPC graph, and this is statistical process control graph, it shows you that your process is out of control while actually it was still in control. And you have rules that you use that take some time, that also do not detect every time that your process really does go out of control. It doesn't immediately detect it because you balance how strong it is in detecting when there really is an error versus how it does not give you a signal when there is nothing to signal about. And this is, for many tests, a balancing act. If you have very good analytical methods, very good so many of generation tests, then the balancing becomes less. It really depends on what area you are in, what type of test, how easy it is to do, how clear-cut the answer is. And then, some of the tests, they are so high in the percentage of getting the correct answer that it's almost no balancing act anymore. Some tests, unfortunately, really force you to make a decision. And I mean, we've had quite a lot of discussion about this also in the recent COVID pandemics, the testing we did then. It has the same problem. We have it in statistical process control, we have it in laboratory studies, we have it in lots of microbiological studies, also in food products, things like that. And today I just wanted to take, and it's a bit of it's a loaded example, but I think it will drive it back home in a good way, because here we do know the population statistics a bit, and I think it gives you a window into how to make these decisions about when to test, but also what value to put on a test result. For this example, I did not take a typical standard process control thing. I actually took the data that fits with an HIV test. So this is the test that shows if in your blood serum you are positive or negative for HIV. And this is the last generation of tests, so not the current version is slightly better. This is, let's say, the one from 15 or 20 years ago. And what they said back then is that we have a precision and a detectability of 99.6%. Now, what does that mean? A detectability means that when you are really positive and you take a test, then the test will say positive in 99.6% of the cases and will say negative in 0.4% of the cases. Now, the precision of the test, that one says if you were actually negative, the test will say negative in 99.6% of the cases, but it will also say positive in 0.4% of the cases. Now, this concept you have in many chemical and basically all microbiological tests. There is always a chance that if the actual sample, so the truth, was positive, the test will still give you negative, or the other way around. And we're talking about type 1 and 2 errors here, but basically the things you want is, if it's positive, the test needs to say positive. If it's negative, the test needs to say negative. Now, based on these numbers alone, you would say, well, that is a wonderful test. And actually it is. I mean, it is a really good test if you have only these numbers. There are tests that are way worse than this, and yes, also for diseases. There are tests that are way worse than this. But if you just look at it without thinking much further, then what you see when you do one of these tests is you don't see the truth that's in your blood, right? You see either a positive or a negative. So let's say you were pretty unfortunate and you got back positive result. Does that mean that you are now 99.6% sure that you are HIV positive? Luckily not. But how to explain that? Now that has to do with how prevalent is it actually in the population? So if you have no real reason to assume that you are really in the positive category, but you just sort of randomly take the test, so screening tests, much like we have been doing quite a lot over the last 2 years, but then not for HIV, but for COVID. Screening test where you simply screen everyone, then you have to take into account what is actually the possibility of getting someone who is really positive into my test system. And we're going to check what is the chance to get a positive result. So if there are 0.0% of people that are really positive, and these are the statistics for the Netherlands. Okay, we don't really have a screening program, which I'll get to in a bit, so maybe it's slightly too low, but it'll be around 0.2%. And when you test those people, you are 99.6% sure that you will get a positive and a little bit for a negative. So let's just round that still to only 1 decimal. Now for the negatives. So almost everyone in this population is actually seronegative. So most of them will get a negative score result, but also 0.4% of 99.8% will actually get a positive test result. Now that means that if you randomly screen people, what you're getting back is that, and of course most of the test will be negative, but that part of the positive test result, as I just said, if I get as a random person back a positive result, do I have a 99% chance that I'm positive? Well, no. If I am a random person, I actually have a 0.2 out of 0.6. So I actually only have a 33% chance of really being zero positive. Because the population, and we're assuming that I'm just a random bloke, has a very high percent of negatives, of real negatives, and a very low percent of real positives, these seemingly small percentages, these analysis errors, these type 1 and type 2 errors, they result in the end, there being fewer actually positive people amidst all of the positive results than there are actually negative people. Now, this is of course also why in these test setups, one result does not determine the outcome. What they basically say is when you have one negative, well, we'll completely let it rest, but if you have one positive, we're going to retest, we're going to do different things, because we are not even 50-50 sure that we've got a real positive. This is also why in many laboratory studies you have an extra round of testing. You have counter expertise samples. You have let's check if it's an anomaly, and to have things like out of 5 samples I want at least 2 to be positive. Things like that are built in because we know that these errors exist. And this also is very important when we do any type of analysis, and especially the microbiological ones, but any type of analysis based on probability and based on statistics in industry. When we do our SPC charts and we get one hit over 3 standard deviations, don't immediately change your process. Take it as a very strong signal that you have to go and investigate. Now, if you get it again in a short while, the chances are becoming slimmer and slimmer that it is a false positive, and it really does become a good reason to go and adjust things. But basically, the first alarm that you get is mainly a go and check, go and see what is happening type of alarm. Now this is also, and then coming back to the Dutch and HIV example, a reason why the Dutch health system actually does not do any screening testing on HIV. And even when you go to a GP or some healthcare facility here in the Netherlands and you just want to do a test, they will tell you, no, if you are not in one of the higher risk groups, we will not do a test with you. And they sometimes explain it like this, usually not. They just say it's procedure, but the reason why they will not do it is not based on that it costs so much. It is based on the chance of getting a positive result and then not really being positive, and that creating a lot of stress and a lot of pressure is so high that they do not want to do that. Now that is different from some other countries, and I mean the place to debate whether it's smart or not is probably outside of this channel, but still there are also countries where, for instance, every immigrant has to do a test, or where you do these type of tests just because you are part of the working population. And it means that, well, okay, you will focus in on the actual positives a bit quicker, because of course this whole group here, if you screen them a couple more times, so confirm the test a couple more times, you will pick up people sooner, but you're also going to have a lot of people that get a false positive. Now that, if we're talking about this example of HIV, of course has a major impact on a person's life. In industry, the things we usually talk about in this channel, the impact is a bit less. I mean, we're just checking if our machines are still doing the correct thing, or we are maybe scrapping a batch of product that actually was good, but the test showed it was not good. So, we're not talking so much about human lives here, but still, even, within how we normally plan within Six Sigma, within the whole industry, our quality control systems, how we work with this positive and negative effect of testing, it's an important factor to take into account. We know that not every test can be trusted, and we often use a bit cheaper test methods, or we're not going to extend the sample group so high that we're going to get to even these numbers. So we're very often accepting much lower quality tests, and that means that these measurement errors, they will be in our system from time to time. And that is good to know. It is good to know that, well, we will not be taking risks if it is about food safety or something like that. We'll just scrap a batch if we get bad results. But in all of the testing that we do, and SPC is an example of that, you will get false positives. And that means that you have to bear in mind, when you get a positive result, don't immediately change the process, don't immediately throw away your product. This is a strong signal that we have to verify. Only the testing, only the statistical anomalies, they by themselves are not enough to just take the decision. It is one of the tools that we use, and it is a powerful tool to check again the process and see if we need to make adjustments. Unfortunately, the other way as well, if you get only good results, it still doesn't mean you can sleep, although usually we put our testing systems in such a way that we try to minimize this. It is actually positive and I'm getting a negative. So what you often see in many tests is that this will be roughly the same, but here we have a much bigger difference. For instance, we accept that 5% of the actually perfectly okay products will give a positive signal, as long as of the actually problematic things, almost nothing goes through. We catch the problems when they are there, and we sort of accept that we get an alarm from time to time, take some precautions when maybe, truthfully, it wasn't completely needed. Anyway, that's what I wanted to share with you in this video. It's an example outside of the usual Six Sigma industrial improvement zone, but I think it really drives home this idea that if you know that usually everything is okay, then this rather small measurement error can still make that the ultimate result from your analysis doesn't tell you a lot, and you really need to keep your eyes open. Now, if you like this, don't forget to hit that like button. Let me know which other topics, within Lean Six Sigma you would like me to comment on. And for now, I wish you the best of luck in your Six Sigma journey. And as always, don't forget to enjoy those improvements.